So hello everybody and welcome to this week's SEDS Online webinar. As always, we'd like to thank our sponsors from IAS, which allows us to offer all of these resources free of charge, including the recorded lectures, learning tools, and even virtual field trips. So make sure you take a look at our website to see all the new info we have on there. Today's lecture is by Dr. Elda Miramontes, who is an assistant professor at the University of Bremen. She got her master's from the University of Vigo, her PhD from the University of Western Brittany, and her research interests are in sedimentary processes that control seafloor morphology and sediment distribution in the deep sea, with a special focus on deposits generated by oceanic currents and ocean circulation to improve paleooceanographic and paleoenvironmental reconstructions based on sedimentary archives. So I will give the floor over to our presenter, and just a reminder to leave your questions until the end when the chat is open, and make sure you post them to everybody, and we'll go through those. So over to you.
Yeah, thank you, Simone, for the introduction, and thank you everybody for joining this talk today. So let's start with it. Yeah, so today in this talk, I'm going to talk about contourites that are the deposits formed by the oceanic circulation, and also about the currents that form these contourites. So first of all, let's jump into the deep sea. The deep sea was for a long time considered a zone that was very quiet with very weak currents, and most of the sediment transport was supposed to be controlled by gravitational process, as we see here. For example, like there was some turbidity currents flowing down, and this will be the main transfer of sediment to the deep sea. But with time, especially in the 60s, there were some revolutionary publications that showed that actually in abyssal plains and deep sea floor, there are many indicators, many sedimentary structures that show that actually the bottom currents they are strong enough to generate sediment transport and generate different features such as ripples, lineations, or scours they observe. So these first studies related the formation of these deposits that they call contourites to the currents that flow along the slope and that are related to the global overturning circulation, to the thermohaline circulation. And these currents mainly flow along slope, and they generate in some areas very large sediment bodies. For example, in here, as in the northern Atlantic, near Florida, you can even see in Google Earth this huge sedimentary deposit that were already investigated at that time, and where you can see here in a cross section across this body, these huge sediment deposits that are related to these currents. And because these currents mainly flow along the bathymetric contours, they are named contourites. But then this definition evolved a little bit with time. So now we consider contourites all the sediments that are deposits or substantially reworked by the persistent action of bottom currents. So in here, there are some concepts that are already important. First, there can be any type of sediment that is affected by currents. Also, doesn't matter the water depth, because before it was mainly referred to deep water environments, but actually there are also contourites in lakes and in shallow environments. And then also the persistent action of bottom currents. So we have the term bottom currents that refers to all types of oceanographic processes that can affect the seafloor. So not only these currents that are related to the global circulation. So for those that are not so familiar with contourites, I would like first to do a brief introduction about what are contourites, how they look like, and how they are formed. So because usually when we think about contourites, we think about these large, muddy sediment bodies that we can find in abyssal plains or in continental rice, but actually contourites are very diverse. And they also include sandy deposits that are mainly formed by winnowing of the fine material. And then also these systems include erosional features that we can find in zones where the energy is strong enough to erode the sediment. And we have, for example, in this area, we can have furrows, channels, moats, scours. And now I would like to show you some examples. Here you can see some separated mounded drifts and moats. Both of these features, erosional and depositional, are often related together. So these separated mounded drifts have a mounded morphology, and they are bodies parallel to the slope, and we commonly find them at the foot of the slopes, either at the foot of continental slopes or seamounts, and even often in between seamounts, we can find very small deposits that are confined in between these topographic highs. So we can have moats or channels, and the difference is mainly that in a contourite channel is more erosive and we have more truncations. So it's not only dominated by erosion, it can be also non-deposition in this environment. Then we can have other types of very large deposits that can be detached mounded drifts. So in this case, instead of being parallel, the body is perpendicular to the slope. And because there is a current that detaches from the slope and generates a deposition in the middle, we can find this type of deposit, for example, in the Eroded drift, or this is another case here from the Mozambique channel. And on the top of these deposits, we can have other bed forms, for example, sediment waves, as we can see here and here a bit closer. And these sediment waves can be either on the top of larger drifts, or they can also cover large areas of the abyssal plain, for example. And another typical contourite drifts, or different types of contourites, are the plaster drifts that have a convex shape morphology, and they are often associated with contourite terraces. Contourite terraces are relatively flat surfaces on the top of plaster drifts. They can either be maybe not so flat, but in some areas, particularly such as in the Argentine margin, they can be very large and very flat, and they are often dominated by erosion in some areas, and they are mainly sandy, while the part of the plaster drift is mainly muddy deposits. So also on the top of the terraces, we can often see erosional features such as moats or channels. In the areas where the currents are very intense, we can also have large surfaces that are eroded, and we call them abraded surfaces. Here you can see an example from the Argentine margin, where in between the terraces there is a large area that is totally eroded with abundant truncations. But then we can also find it on the seafloor, the basin floor, where the whole basin is just completely eroded, as in this case from the Mozambique channel. So now the questions that I would like to try to answer, or at least discuss during this talk, are how, when, and where ocean currents control sedimentation in deep water environments. And how the currents control the sedimentation is also important to know. First, what's the distribution of these currents in the environments where we find the contourites, and also what's the variability of these currents. So already in the early studies from the 70s, 80s, when there were this acquisition of data in the Atlantic, mainly with also measurements of current velocity and also concentration of suspended sediment, they found that the currents in the zone of the moat is where they are the highest. So mainly there is a current that is flowing along the slope, and because of the Coriolis force, the becomes attached to the slope, let's say. In this case, for example, we have a current that is flowing into the image, and then because it's in the northern hemisphere, it's going to be moved to the right, and the zone with the maximum velocity is going to be closer to the slope, and then the deposit is going to be formed in the adjacent zone that where the velocity is already weaker and sediment deposition is already possible. So what they found is that in the zone of the moat is where the velocity is the highest, and also there is a high abundance of sediment in suspension, but the velocity is so high that this sediment cannot be deposited. And then the sediment is mainly deposited here in the adjacent zone where there is still sediment available, and the currents are already weak enough to allow them to be deposited. And this is how these separate and mounted drifts are formed. The detached drifts, they are formed usually in between two currents that flow in different directions, or sometimes in one direction. But in the middle, there is a minimum velocity. And this is in the zone where there is also abundant concentration of suspended sediment, and the currents are weak. So the sediment can be mainly deposited and concentrated in this area. So here is another example of the same pattern from the Mozambique Channel. This is this lower slope of the Mozambique Channel and of the Mozambican slope. And here there is a moat and separate mounted drifts on the right. And here you have in the same area model bottom currents. This is the average, the mean speed. And you can see there is a zone that is the Mozambican undercurrent that flows towards the north in this case. And because it's the southern hemisphere, then Coriolis force puts it to the left. And we have mainly the erosion on the left part of this profile. We have a broad surface, a moat, and then we have a zone with less currents, so weaker currents, and we have the deposition of the drift on this side. So we go from more energy to less energy in the zone where we have the drift. So now I'm going to show you another example of some measurements that we did in the Argentina margin. So this is a zone that is located in northern Argentine. It's a zone of the confluence between the Malvinas current that flows towards the north and the Brazil current that flows towards the south. And in this area, there is a huge contourite system that consists of different terraces, erosional surfaces, and plaster drifts. So it's a huge variety of contourites in this area. And now I'm going to show you some of the vessel-mounted ADCP measurements. So these are measurements of the current velocity that are acquired from the vessel while it's moving. And here in this map, these are the surface currents. So you can see that they are relatively intense. So they can be more than 50 centimeters per second, and they flow here towards the north, the Malvinas current, and then here towards the south is the Brazil current. But when we have a look at the near seafloor currents, they are already a bit weaker. But there are some zones here in pink and red that where the currents are still high near the seafloor. And actually these correspond to zones where we see the abraded surface and also some moats. And inside the moats, we reach velocities that are around 30 centimeters per second, in some areas even a bit more. And also in the abraded surface, the currents can be relatively high. So in average 23 centimeters per second, sometimes more. And well, this is part of a publication by Henriette Wilkens and colleagues, and this should be soon available. And now I'm going to show you a profile that goes through here so that you can visualize better how these currents are distributing in the different features. So here we have the two terraces and an abraded surface in the middle. And what you see here in color is the average speed from reanalysis, a model that incorporates also measurements. And here you can see that in the zone where we see the abraded surface, there is a core of the current. The Malvinas current is mainly flowing along here, and that's why these strong currents are affecting the seafloor and eroding exactly the seafloor. And what's also interesting here to note is that we have different water masses in these areas, in the surface, the Antarctic intermediate water, and the upper Siquipora deep water. And actually, because very often when we interpret from the geological record, the contourites, we talk about water masses and how they are moving, but actually what forms the contourites is the currents, and not every water mass can be related to a single current. So we can have currents that are affecting different water masses, such as here, for example, the Malvinas current incorporates different water masses, and also we can have different currents, different cores of a current within a water mass. So they are different things and they should not be mixed together. Yeah, now I'm going to show you some ADCP measurements we have from the area here where we have a moat. This is the moat and a small separated mounded drift. So in here you can see the speed measured with the ADCP data. And you can see that near the surface, there is a maximum of velocity and then it decreases. But then near the moat, near the seafloor, there is an intensification of the current. So we have still, again, here, high currents. This is not something local. When we have a look at the profile that goes along the moat in here, that is this one, you can see again near the surface the strong currents, but also all along the moat, we have stronger currents that at intermediate levels. And this happens only inside the moat. When we have a look at a profile that is farther upslope, outside the moat, actually we don't have these intense currents near the seafloor anymore. We just have them intenser near the surface and then decreasing with the depth. So to summarize, in the previous one, we had the moat where we have the strongest currents and then a separated mounded drift that is formed in the zone of weak currents right next to the moat. But in the case of the plaster drift, this is a bit different. The plaster drift usually are formed in zones in between two currents. So we have these features that have a convex morphology, the terrace. So we have one stronger current here. And the foot of the plaster drift, we have again strong currents. And very often we can even find a moat in this lower part. And here you can see very clearly, this is an example from the Mediterranean Sea. And these are model bottom currents. And you can see in the middle of the plaster drift is where the currents are the weakest. And then there are two zones above and below this central part where the currents are strong. So another question is when are contourites being formed? So the definition of contourites, it says that they are formed by the persistent action of bottom currents. And this is suggested because we can see the sediment bodies that are being formed for a very long time in the geological record. So for example, here you can see one contourite drift from the Gulf of Cadiz in the southwestern Iberian margin. And this drift started to form in the Pliocene and is being formed so far until now. And this shows that the oceanic circulation was established at that time, and then the circulation continued to be active. And that's why we tend to refer to this persistent action of bottom currents. But even when we have a look at the deposits a bit more in detail, we see that these deposits are not just simply continuous. Very often we see cyclicity in the deposits, and actually the typical facies model for contourites is the bigradational sequence that shows some coarsening up and fining up sequence, and this is interpreted as representing change in the current velocity, that there is an increase in the velocity and then a decrease. And all these changes can be controlled by tectonics in a longer period of time, or by climate and or sea level. And what we usually do is we have this geological record, and we tend to interpret based on these observations what were the changes in tectonics, in climate, and sea level. But actually what is changing are the currents. And that's what we are missing a little bit to really know exactly how do tectonics, climate, sea level change the currents, and how do the currents change the contourite. Because actually the currents are not something stable. The ocean moves at different frequencies, and there are very different types of processes that are going to control the currents that are flowing near the seafloor. And that's why also in the modern definition of contourites is included the term bottom current, that actually this just simply refers to any type of current that is flowing near the seafloor. So we can have the typical along slope contour currents that are related to the global circulation, but we can also have barotropic and baroclinic tides, internal waves, then shelf water cascading, and eddies. And I would like to here now talk briefly about the shelf water cascading, because these are events that can be relatively short in time, but they can have a very profound effect on the circulation of some areas, and also on the formation of contourites, especially in the Mediterranean Sea. There are three main areas of dense shelf water cascading: the Gulf of Lions, Adriatic Sea, and the Aegean Sea. And they are mainly formed, these events, in winter, because there is a heat loss due to strong northern winds, and this makes that the water on the shelves becomes very cold and then dense, so it tends to sink downslope. So there were some monitoring studies in the southern part of the Gulf of Lions near Cap de Creus. So in all these points, they were measuring Palanques and colleagues. They were measuring the temperature here in blue, the current speed, and then the suspended sediment concentration in black. So you can see that during these events that can last several days or more, the temperature sinks, and then related to that, there is a strong increase in the speed that can reach 1 meter per second, really high speeds. And then related to that, there is also an increase in suspended matter, suspended sediment concentration. So these events can have a direct effect on the seafloor. In this area, it's being observed, there are furrows, sediment waves also in this area. So there is a strong direct effect. But this is not only the direct effect, what is important, but it's also controlling the whole circulation in the deep ocean, or in the deep water of the Western Mediterranean Sea. And here you can see some model outputs during the month of March 2013. So this is the temperature. There was some dense shelf water cascading. At that time, there are cold waters sinking and then flowing along slope. And then related to that, there are also very strong currents flowing here along slope. But not only in this area that is directly affected by this process, but also on the other side of the basin. And here, during that time, we also have stronger currents flowing along slope. And actually in this area, you can see here the profile, there is a moat and a separated mounted drift. There is the Minorca drift in this area. So that means that actually these events of dense shelf water cascading are activating the currents in the zone that are opposite of the basin, and maybe also favoring the formation of these contours. And actually that's something very important, because especially in the Mediterranean, there is a strong seasonality in the currents. So in winter, the currents are much stronger. You can see here, also in the zone where we have the drift. But in summer, they are very weak almost everywhere. And actually the zone of the moat in summer could be also under weak currents. That means that if there is sediment arriving at that time, the position will be possible. But during winter, the moat can be eroded, and at the end is the result. So this is not a continuous process. It can be variable at very different time scales. And also eddies are very important processes that can affect the seafloor. The currents, they are often not laminar flows, very calm, but they show very often strong mesoscale instabilities. Here you can see some modeling from John Gula, who is the barotropic vorticity in the Gulf Stream. So here's Florida, the Bahamas banks, and here is the Gulf Stream moving northward. You can see all the eddies related to this current. So you can imagine that when all these currents are flowing, the effect that they are going to have on the seafloor is not going to be all the time the same, because the position of these eddies is going to change very rapidly. And here in the zone of the Bahamas banks, there are many contourites. So here you can see them in orange. There are some contourites here between Florida and Bahamas, and then related to the corners of the banks, there are also large deposits. So here in the model, you can also see how unstable are these currents in between the banks, because all these topographic changes are strongly affecting these instabilities. So all the deposits that are going to be formed here are going to be affected very differently by currents, depending on how these instabilities are evolving. And when we have a look at this idea, but in a larger scale, we can see from the results of Amanda Tran and colleagues, they did some modeling in the whole ocean of bottom currents, and they analyzed what's the variability of these bottom currents in the ocean floor. So the zones where there is this high eddy kinetic energy, that means that there is high variability. Actually, this eddy kinetic energy is much higher in the zones of contourite systems that are these yellow zones than in the rest of the ocean. So it seems to be that the contourites are especially formed in zones where currents are not very continuous and persistent, but there is a high variability. And this variability can also be in very short term, so high frequencies. We did some in situ measurements of currents on the top of seamounts in the Mozambique Channel. There are some drowned platforms in the center of the Mozambique Channel that are in some areas covered by sand dunes. And in these measurements, we have here the speed of the current and also the turbidity measured near the seafloor, and the temperature. So what we saw, there were huge changes in the velocity at tidal cycles. And there are in some periods of time where there is almost no current, almost zero. And then sometimes it increases to 40 or even more. And it's during the time of weak currents when we have an increase in the turbidity. Because when the currents are very strong, they just transport away all the sediment and it cannot settle near the seafloor. But when the currents stop, then the sediment that is in suspension in the water column can start settling down, and we have this increase in the turbidity. But apart from, before I just showed you 3 days of these measurements, but here I'm showing you the whole record, 1 year in the center of the channel. And as you can see, there is high variability. So we have these high frequencies related to tides, but then we also have periods of more intense circulation. And what you see here, the orange line, is the threshold to erode the sediment that we found in this area. So you can see that this threshold is not reached most of the time, but there are some periods of time where it's reached. And actually, for example, here, at this moment, this was a moment where there was a large anticyclonic eddy passing by, and was the side of the eddy right on the top of the site, and that's why the currents were so much stronger. So when the eddy moved farther south, and then was everything already more calm, and the currents became weaker again. So during this moment, when we have the highest velocities, this corresponds to a moment where we had an eddy, the general circulation, and also the tides that were favoring the accumulation of this high velocity. Because even when the eddy was there were some periods of time when the tide was playing against the currents, that the currents were still weak. So maybe most of the sediment is just being transported during some periods of time where the combination of different processes is going to generate stronger currents. So the question is also, how can we then interpret that in the geological record? Can we know if the currents are just what we preserve is the long-term variation of these currents, the mean circulation, or we are just preserving these events of a short duration where we have the accumulation of different processes that are transporting the sediment together. So the question is, we need to have a look at the contourite systems at different scales. When we have a look at a basin, in a large scale, we are going to find first the large contourite drifts that are commonly formed by the general circulation, large scale, and form a long slope. And then when we have a look a bit more closer to these features, on the top of the contourite drifts, we can find smaller scale features, for example, some channels, ripples, or even lamination and particular smaller scale sedimentary deposits. So we have the larger drifts, for example, like here, the contourite terrace with the plaster drift that are mainly form a long slope and can be probably related to the thermohaline circulation, to all these currents that are more or less stable in time. And then when we have a look a bit closer, we are going to find other smaller scale features, ripples, channels, that sometimes even have different orientations. And that's already very helps us to understand if they are related to other processes, because sometimes we can find, for example, dunes that are formed migrating upslope and have other orientation that suggests that it's not being formed by the long slope currents. And these type of features can be formed, for example, by tides, mesoscale eddies, or internal waves. I'm going to show you one example here of these small scale features inside a moat. This is an example from the Argentine margin, what I showed you before already. So inside the moat, there is a scour related to a escarpment on the slope. And we measure with the adcp a small eddy in this area, cyclonic eddy. And even in the model also, we could see that very often there are cyclonic eddies being formed behind this escarpment. So it can be that the interaction of the current with this small escarpment is generating some instability, some eddies in this area that favor local erosion. And then internal waves are also processes that are relatively short in time, but that can have a strong impact in the seafloor, and this impact can also be recorded in the form of wet forms and also erosional surfaces or channels. So it has been Drogi and colleagues, they found that the dunes that are formed that are found in the Messinian Strait are probably formed by the interaction of the internal waves, internal solitary waves that then interact with the seafloor and form these dunes. And also in the South China Sea, Ma and colleagues found there is a huge area with bed forms and also channels that they relate to the shoaling of internal solitary waves, and also to internal waves that internal tides that move up and down slope. So in the Mozambique channel, we also found a big channel in the upper slope that is very continuous, very straight. And we suggest that it's being formed by internal waves that we also observed in the area, that they are trapped by barotropic currents, by the tides in here, and they become trapped and they are going to affect the seafloor for a longer period of time, always at the same place, and that's why it generates these channels. And we found them at the present seafloor, but we can also find it in the subsea floor, and this corresponds to the previous sea level heights. So the currents are everywhere. So the whole ocean is, of course, moving continuously, and there are many different zones and regions in the world where the currents are intense and could, in theory, affect the seafloor and form contourite. And the question is, why don't we find contourite everywhere in the zones where the currents are strong? You can see here in yellow the main contourite drifts that have been identified in the world. So they are mainly in the Atlantic, but there are also other zones. So why don't we find more of these large deposits? Well, to form a contourite, what we need is a relatively strong velocity, and also strong currents, but also not too much sediment. So we need sediment so that the contourite can grow. But if there is too much sediment supply direct from the continent, this is going to kill all the contourites, because in these areas it's going to be dominated by gravitational processes that are very powerful events that are going to dominate against the contourites in most cases. So that you can visualize that a bit better, I've chosen this area of southwestern Europe and northern Africa, where you can see in red all the canyons, and then in orange the main submarine fans, and in yellow the main contourite drifts. So as you can see, most of the contourite drifts are actually found in intraslope basins, and also in zones of the slope where there are not many major canyon systems. And this is because when we have too much slope instability and gravitational processes, the contours are going to be destroyed in time. And to visualize that a bit more in detail, there is a very good case in the Tyrrhenian Sea to see this separation in between turbidite systems and contourite systems and how they can grow together but separate at the same time. So in this area, there is a larger turbidite system that's going to this confined basin from Corsica, is the Golo turbidite network. And then on the other side, there is a whole contourite system. And actually, this other side of the basin is doesn't have a direct sediment supply, because the shelf is very large and there are no major rivers in this area. So even during low storms, there isn't much sediment coming directly from this side. So all the sediment, or most of it, that is deposited on these contours is coming from the turbidite system, and then it's being retransported by the currents and finally deposited in there. So the currents are strong in this case in both parts. There are some gyres here, so we also have a strong currents in the western part, but we don't have major contours. We only have a small plaster drifting here, but nothing very large. On the opposite, the other side is purely contouritic. And that's the key question, is sediment supply, not only the currents. And then the currents, they are going to affect also the morphology of the margin. And that's something that has been shown very nicely by Mosher and colleagues along the eastern North American slope. They found different areas with different slope morphologies. And when the slope is dominated by gravitational process, so turbidity currents or mass failure, the slope has a graded morphology. But when contour currents dominate the position, then the formation of these drifts generates above graded slopes. So it's like a plaster drift with this convex morphology, or stepped slopes. And this is typically also when we have the terraces and the plaster drift below that is going to form these particular shapes. So the contours can affect the morphology, but also the morphology and whole structure of a margin is going to control strongly the bottom currents. And then the bottom currents are also going to control the position. So here we have a very clear case. This is the Erik drift in southern Greenland. So you can see here that in the tip, there is on this side the Erik drift. And this is formed here when the currents that are flowing along slope, then they reach the cape and they detach from the slope because there is this strong, faster change in the slope morphology. And then they tend to deposit the sediment in here and then flow again. So this forms this detached drift. So the structure is going to control the currents and then also the deposition and formation of the drifts. And this can also happen even at a larger scale, at a whole basin. And this is the case in the Argentine basin, where we have the Malvinas Falkland Ridge in here, constraining the basin, then the slope, and then the Rio Grande Ridge in the northern part. And then we have this basin in the center that is deeper. And in the center of this basin, there are very large deposits, the Sapiola drift in this case. You can see here the profiles crossing the deposits in the middle of the abyssal plain. And on the top of this Sapiola drift, there is an anticyclone. So there is a gyre here. The currents are moving around the drift. And then this is probably also favoring the deposition of the drift. But the question is the current turning around because there is a drift in the middle that also changes the morphology and therefore it changes the currents? Or is there a drift because the anticyclone was there? So we always have a bit this problem when we investigate contourites and the currents that form them when we use the present day morphology, because we already have the morphology. So we also have the contourites. So we have this chicken and egg problem. What was there first? And actually, what I think is that what happens is we have a positive feedback. So what we commonly observe is that when contours start to form, so for example, we have here a separate mounded drift and a moat. This feature at present day seafloor is very deep and very mounded, but at the beginning, it wasn't so deep and it wasn't so mounded. And this was increasing with time, it was becoming more exaggerated. And this is probably because when the current was at the beginning here, it started to form this moat and this mounded shape. And this then created a morphology, and the morphology affected locally the current again. And then there is this positive feedback and the feature becomes under stable conditions, bigger and bigger and bigger. And that's also why probably we see these faster currents near the moat in the Argentine margin. So we have a moat, and probably because there is already a moat, this is going to intensify locally the currents. So to summarize, what I would like to say as a take-home message is there has been in the last decades, or since the 60s, a lot of progress in the identification of contours, the description of their morphology and their sedimentary characteristics, but we still don't know much about the oceanographic processes that form them. And actually, what is very important so that we can interpret properly the sedimentary record is that we know when these deposits are being formed, how they are being transported, so that we can create good paleoceanographic reconstructions based on the morphology or on the sedimentary fascias. And actually, we don't know much about the currents because there are very few process-based studies on this topic. There are almost no lab experiments. There are just very few, to my knowledge. Some mixed turbidite contourite interaction, so the interaction of the turbidity currents with the contour currents. Also, some experiments of the interaction of internal waves with the seafloor, and very recently also an experiment that proves that the method of soft double sirt is adequate to interpret the current velocity from the grain size. And the problem is also that not only that there are not many experiments, but also that there are very few measurements and also very few modeling studies that reach the seafloor at in the deep sea. So we need to do more measurements and also do more experiments and numerical studies so that we can advance further in the understanding of the formation of contourites, and so that we can quantify the changes in paleoceanographic studies and not just do a qualitative interpretation of these changes. And this is not only interesting because contourites are beautiful, and of course everybody wants to understand how they are formed, but they are also very important for other topics. So as I say, often they are used as archives for paleoclimatology and paleoceanography. So we need to know how they are formed so that we understand these archives. And also contourites are very often affected by slope instability, and they can be a good deposit as a reservoir or seal for hydrocarbon exploration. And recently, it has also been found that contourites host, unfortunately, the highest amounts of microplastic ever observed so far in the deep sea. And moreover, these zones are typically connected with the particular deep water ecosystems, such as, for example, cold water corals that are very often associated with the contourites. Yeah, so to end, I would also like to thank all the colleagues and institutions where I work that helped me in doing all part of this work that I showed you here today. And I would also like to thank especially Henriette Wilkens, that is the PhD student working in the project of contourites and bottom currents in the northern Argentine margin. Thank you very much. I'm looking forward to the discussion and the questions.
All right, thank you very much. That was a great talk, very interesting. And we already have a question in the chat. So make sure you guys are putting your questions in the chat, saying where you're from, and make sure you send them to everybody, and I will read them out. So the first question is from Oswaldo. Thanks a lot, Elda. Fantastic talk. One question: can bottom currents modify prograding system geometry?
Yeah, actually, there are. For example, in the Adriatic Sea, the whole submarine delta of the Po River is actually elongated all along the continent. And this is induced by the currents that are reshaping the deposits that are transported by the rivers down to the delta. And all these clinoforms are also being elongated along the slope. So it's not just across the slope deposit, but is all elongated along the slope. And in these clinoforms of the Adriatic Sea, they have the wave base level, and then they also have another base level there formed by these bottom currents.
All right, so we're still waiting for a couple more questions to come through, but I have one. So how easy do you think that it's going to be to determine like the paleocurrent directions in the rock record using your modern analogs?
Yeah, so that's always the question, because with the modern analog, we know how the currents are at present, but it's of course difficult to say in some cases if the systems are still active, because in some areas, for example, the currents were stronger during glacial periods. So even if we see the morphology at the present day seafloor, they might not be as active as they were before. But when we go to the ancient record, I guess the key to at least understand the general scale, the general circulation, it would be interesting to do some numerical models coupled with the tectonic movement, so that we see these larger changes in the circulation. That has been shown in some studies already, where they saw that especially the closure of some gateways that controls strongly the circulation in the ocean, and that fits with the periods where the contourites in some areas start to form. And when we go to the very ancient record that is already in outcrops, of course, that's even more challenging. But it's not only because of the reconstruction of the conditions of the currents, but also the paleogeometry of the margin that is important, because as I tried to explain today, it's really important, the topography. And then if you change a little bit, that can make also a big difference already in the types of currents and then where the deposits are going to be formed. And so on a larger scale would be possible, but I guess that these smaller features with the process that have a higher variability, that would be more challenging to do.
All right. So we have a question from Brian. Amazing talk. I really enjoyed it. You briefly mentioned the importance of sediment supply. Can you comment some more about how we might better constrain sediment supply in these systems? It's from Virginia Tech.
Yeah, I think it depends a lot on the area. Because yeah, I say it's just we need a zone with relatively low sediment supply, but we also have some areas where we have mixed systems. So in between the turbidity channels or in between the canyons, we still can see the effect of these currents. And even we can have a mixed system where the whole turbidity system is being affected by the currents is changing its morphology. So I guess there is a whole spectrum of influence of currents. What I was referring here is to have the typical large contourite drifts. We need a zone where the supply, there is not much turbidity activity in a large scale that will remove these morphologies generated by the currents. But yeah, it can be that we have also some in-between cases where there is a mixture of both.
And we have another question from Oswaldo. Inversion of bottom currents are linked to tide influences, or are they more linked to climate change?
Yeah, well, I am not sure what you are referring about the inversion of bottom currents, if it is in the bigradational sequence that it becomes then finer, and this is related to climatic changes. In some cases, yeah. For example, in the case of the Corsica Trough in the Tyrrhenian Sea that I analyzed a bit more in detail, we had these bigradational sequences during sea level low stands. And actually we only had them when the currents were stronger during glacial periods in the region, in the Mediterranean in general. And also the turbidity system wasn't active, because that comes a bit again to the other question. And actually in this area, for example, when the turbidity system is working there with high power, there is so much sediment coming to the area that at the end, even the mud gets accumulated in the drifts. And we only have these sandy layers during the periods of time where there is not so much mud reaching the system. And something similar we also saw in Mozambique, that we have this well, there we don't have the whole sequence yet, but there is this sandy coarsening up sequence that is being formed at present during the high stand. And during the low stand, there was so much sediment supply from the delta directly that is mainly mud that is being deposited there, because the current, even if it was also probably strong at that time, wasn't able to remove so much sediment coming all the time. So if there is some tidal in the deposit, some tidal effect, it can be, but the question is if it is can be recognized afterwards, because there is very often a strong bioturbation in contourites, and maybe if there is even a tidal effect that could generate some ripples, because the accumulation rates are also not so high, this ripple is going to be moved and moved over many tidal cycles, and then bioturbation is probably going to even destroy the structures. So in most of the cases I have studied so far, we don't see any internal or not many internal structures. So even if we see ripples at the seabed, then inside the core we don't see much, just all gone.
Very interesting. We have a question from David, watching from Portugal. Going back to the diagram showing the log sketch of the contourite sequence and the criteria of the fining upwards towards the coarser upwards versus sharp base from turbidites, that is probably of easy application near the locus of the current and where sand may accumulate, already there or transported. What about at drift locations away from the current locus? Could just sediment records be reliable if the morphology cannot be assessed from a seismic profile? On a side note, but related, what is the point of situation about recognizing contourites in outcrops?
Yeah, so in the zone that is farther from the main core of the current, of course, the effect is going to be weaker, but the currents are going to transport also at some extent these particles. So even in what could be considered hemipelagic or pelagic sediments, the effect of the current is going to be a little bit. So almost never a particle is going to fall directly from the surface to the seafloor, because during this movement, the time that it takes to fall, the currents, even if they are weak, they are still going to deflect a little bit the zone of deposition. Then if this is going to be recorded as a particular morphology or not, maybe not, and then we only see these particular shapes in the zones where we have accumulation effect, where we have the stronger currents not so far away that are sweeping away the sediment, and that becomes accumulated more intensively in some point. So if they are reliable for the morphology, well, if there is no morphology, of course, it's a bit harder to identify. That's why, well, usually in the most common classifications of contourites, there is the type of contourite sheet drift. There is just a very flat drift, usually in abyssal plains, but it just becomes a little bit thinner towards the sides, towards the margins. And that's very hard to identify, even especially if you don't have a huge profile along the whole margin. That's why I didn't include it here in the classification today. But I guess that probably if you want to have a continuous record, this would be the best place. Then you always have to decide if you want high resolution and higher accumulation rates, then you go to the drift. But you risk also that there are going to be some areas, some hiatus, especially if you go very close to the moat, because there sometimes the current becomes stronger and might erode some zones. So I'm not sure if I am answering very well the question, or I just drifted also myself a little bit. But then what was the second part? In the outcrops. Yeah, so there has been some great work on outcrops by the team of well, in the Granada Department of Stratigraphy, the University of Granada, and also with Javier Hernandez Molina and his team that have been working in different outcrops from Cyprus and Morocco, and they are analyzing in detail also the ignophases that provide very good information in the environmental changes, if there were also some small surface of erosion or periods without deposition that sometimes are not visible at the structure scale, but these changes in ignophases provide apparently good information to try to identify and distinguish contourites from other types of deposits in outcrops, where in outcrops we don't have this information about the morphology as we can have at the present day seafloor.
All right, next question. Excellent talk, thank you. I have a question. Have you done any mineralogical analysis of the contourites, XRF or XRD? I'm interested to see if any done, some data if it's public domain.
Sure, there are many analyses available from different types of contours worldwide, especially because these are the standard measurements that are done for paleoceanographic studies or paleoclimatology, and contours are often being called for this type of studies, so you can find in many regions of the world. So what we can see typically, for example, is with the XRF data that there is an increase of zirconium and heavy metals during in these sandy sequences, or when the grain size increases a little bit more. So it's just a proxy also for grain size. And then the composition of the contours depends strongly on the area. So actually you can have any type of contours. There are carbonate contours in the zones close to carbonate platforms. We can have siliciclastic contours in other areas with the composition depending on what's coming to the system. So it's the composition is strongly variable, and yeah, it depends a lot. But this especially changes in the concentration of heavy minerals usually provides good information.
The next question is from Valentine in Oslo. A great talk. Always amazing to see the quality of the seismic data you're working with. People have shown that ideas are being very that tides are being very sensitive to the distribution of the continental masses, with basically tides being very weak during supercontinent periods. Do you think you'll have a same supercontinent cycle for contourites? And do you think it'll follow the same trend as the tides, weak during supercontinent periods?
Yeah, it can be. I mean, I'm not very familiar with the contours in very old geological times, but I think that there were big changes, for example, after the closure of the Panama Strait, and there were also many contour systems that were forming after the Cretaceous. So in the Cretaceous, there were mainly turbidite systems dominating, and also mixed contour turbidite systems. And after that, later on, there were some contours that they started to form. So there are probably, yeah, these large changes that can be observed in many regions. For example, the period when the contours started to form in the Indian Ocean, and also in the South American, in the Atlantic, in South America, they were at the same time. So yeah, they are all more or less connected, because at the end, the whole global circulation is connected. So these large systems are mainly related to this global circulation. So if the position of the oceans doesn't permit this global circulation, of course, there is not going to be a big formation of contours. And the same, so for example, in the Mediterranean, when the Strait of Gibraltar was closed, there were also no contours around the Iberian margin, and they started to form where there was the Mediterranean outflow water coming out of the Mediterranean and then flowing around the Iberian margin. Yeah, so they are related, yeah, to these larger tectonic events.
Our next question is from Kurt in Zurich. Thank you, Elda, for a stimulating talk. He's got, it looks like, 2 questions here. Is there an optimal density of sediment particles that form stable contourites? And are you aware of contourites in sediments with a high organic content that will make the sediment particulates significant or specifically lighter? So like high biological productivity areas like lakes or different current systems.
Yeah, I wouldn't say there is an optimal density for stable contours, because we can find contours made of bioclast, and light carbonate sediments, and then we can also find contourites mainly made of quartz. So I think this is not a limiting factor for the contourites. Maybe this could change a little bit the shape or even the currents that you need to transport these particles. That could be a bit easier. So, but that's something that we don't know yet. But it could be that you can find contourites in an area that is mainly dominated by carbonate deposit that could have weaker currents to form the same contourites as in another area that will be dominated by quartz. This is pure speculation, but could be. We will need to test that, but it's possible. But I guess it depends because the range of currents is also very broad. So at any place at the end, probably you're going to find a zone where the currents are strong enough to also transport heavier material. And then concerning the organic content, for example, usually in the zone of the Benguela current or the larger upwelling systems, even if we don't find there the typical large contourites, as we can find, for example, on the other side of the Atlantic, there are still contourites and there are often plaster drifts, and especially in the zones, actually in both of them, in the Benguela and also in Mauritania, there's also an upwelling system. There are many cold water coral systems and cold water coral mounds, and around these sea mounds, there are also often contourite deposits because the mound generates, again, like a topographic high that is going to affect the currents, and around there are also contourites. So in this case, I don't know exactly if the organic content is higher, but it could be that is higher than in other areas. But let's say that these types of environments are not the typical ones where we find the very large contourite drifts. We can find the smaller ones that maybe, I don't know, could have also higher organic content. But it can be also that in the zone, if we are close, it depends on the area where we are of the system. If we are in a zone where the currents are very strong, mainly inside the moat or in a contourite terrace that is also sandy, usually the organic content is lower in this area because especially we find finer material, so it's all, the organic content is usually with the fines and it's all gone. And we see that very clearly in the Argentine margin. We have some cores in the terrace, and at present we have a sandy material with very low organic carbon content. But then in further down in the record, there are some layers with finer sediment, so it's mainly muddy sediment, and there the organic carbon content increases strongly. And this is also commonly related to sea level changes because these contourites are on the slope. So when we have these periods of time with accumulation of fine material, usually it's also during sea level lows and when the coast is not so far away. So we have also more direct supply of organic material from the continent or from shallow waters that is accumulating faster.
All right, our next question is from Sophia in Yale. Thanks for a great talk. Do you think, or would you expect, that the overall prevalence of contourites changed substantially through the late Cenozoic, specifically with the start of southern and northern hemisphere glaciation?
Yeah, there are some strong changes, but the circulation remained more or less the same. Let's say the current was, the distribution of the currents was similar. It was mainly the intensity of the currents that changed. And that has been observed in different zones that the intensity of the current changed, but we don't see major hiatus or like the whole deposit changed and we have a new type of depositional system. So during the last glacial cycles, let's say, there were these changes, and maybe sometimes in some areas we could have more gravitational deposits if the coast was closer, but the whole circulation system remained similar during the last cycles. But yeah, if we go a bit farther back in time, yeah, then might be big changes, and the main changes are related to the tectonic processes mainly, and the climate can change it, but because the shape of the margin remains more or less the same, at the end the system remains similar.
Excellent. So that's the last question we have in the chat. So thank you all for coming to this week's talk. Next week's seminar is at the regular time, 4 p.m. UK time, when Jillian Apps and Frank Peel will be talking about early Pleistocene mud tectonics and sedimentation. So we'll see you all then, and thanks again, Elda, for that great talk.
Yeah, thank you very much for the invitation, and thank you everybody for the questions, the discussion, and for being here.